I didn't check the screen, and I recorded only my voice, so that was a bit awkward. So now here, hasn't turned in? Great. Thank you. Now, okay. Okay. Do you know what's this?
Oh yes, it has a name. I've seen this before.
This is a modern rot. On the left, it's the modern rot set. The other is one of the Urea sets. Okay, so yesterday there was also one student present. So this is a very familiar, what is it, class. Okay, I told her that I have very serious problem with the material that I taught you in the syllabus. It's too hard for a chemistry student. Even for a physics student, it's too hard. For example, we reached some rotational groups, transformations and everything, and it is for particle physicists. It's MSc or PhD level, doesn't matter. So very quickly, do you remember orthogonality and you know the basis?
Yes.
So we had coordinate transformation, vectors, free vectors, for example, 3D. Okay. It has a special case when the vectors are perpendicular, and the perpendicularity has a generalization called orthogonality. The perpendicularity is two vectors are perpendicular if you have a scalar product and the scalar product is zero. You can define the scalar product in different way, or multidimensional space, and then you also expect that two vectors from a space is perpendicular. Not perpendicular, the product of two vectors using that generalized scalar product is zero. Then we call this orthogonality. And if the basis vectors are orthogonal, perpendicular, if you say perpendicular, think for perpendicular and say orthogonal, that's fine, then it's an orthogonal basis. If the basis, the length of the basis vectors are one unit, they are normalized. It's very simple. You have a vector and multiply the length of the vector. Then when you have free unit length basis vector, then the basis is, and we are orthogonal, when they are orthogonal, then that is orthonormal basis. And the shortcut is OB and ONB. Yes. Okay. That was the stuff yesterday. You can prove the independence of orthogonal vectors. There are long proofs and deductions and everything you can find in the book, which is written in Hungarian, but I cannot do anything there is something called best approximation. Have you ever heard about the least square method? Least square method. Least square. You have laboratory exercises, and you use this paper. Seriously?
Yes.
Yeah, actually, this is shocking to me. If you have points measurements with error, you can fit a function, for example, a line. Do you know what I'm talking about?
Yeah.
And there is a method, a very simple method, it's called the least square method. And there is something similar to this in the books and in the lecture. But I skip it because it's too much. Let's do not skip the following thing. Orthogonal and semi-orthogonal matrix. This means the following. You have a matrix, any matrix, and you divide it into vectors. If these vectors are orthonormals, then you say the matrix is orthogonal. One example. There were yesterday more examples actually. Oh, okay. That is one matrix. Something. And you take this row and this row, and you have two vectors. I have told you we have no restriction. We put together vectors and form a matrix, or we take a matrix and divide into vectors. This is one example. And this vector, I do the scalar multiplication, and that's 0. And the length is 1. So this is an orthogonal matrix, which is not true. Orthogonal matrices are square matrices. This is not square matrix, so this is semi-orthogonal matrix. There are many examples for this. So if you have just your own orthogonal basis, you have this basis, and for example, there are many examples. You made this matrix. Of course, this matrix is orthogonal because here are the original vectors. You also can choose rows, not only columns. And then you have a orthogonal or semi-orthogonal matrix. These matrices has some very useful features. For example, for all matrices, if you multiply the matrix with its transponent, then you got the identity matrix. Here, AT, that's one transpose. So sorry, this is 0. No, I'm idiot. Sorry. This is 1. This is 1, this is 0, and this is 1. That's the transpose. That's 1. So if you do the multiplication, you have 1 here and 0 everywhere. Do it again, then it's 0. Do the multiplication here, that's 0 here, and 1 here. So this is not a proof, a deduction of the thesis, but this is if you do the transpose for any matrix, not only the square matrices, and square with the original matrix, and you got this identity matrix, then that's an orthogonal matrix. Okay, the following definitions of the orthogonal matrices are equivalent. What does it mean? The column of vectors of Q form an orthogonal system. That was the definition. Jump statement 5. The row vectors of Q form an orthogonal system. That's also the definition. The previous thesis is transpose of the matrix multiplied by the matrix, or the matrix transpose multiplied T gets the what is it? The identity matrix. That's the previous thesis. And if you look for this Q inverse equal transpose, if you check the statement 2 or 3 and record the definition of inverse, that's the inverse. What was the inverse? The inverse was that matrix that you multiply the original matrix and you got the eigen matrix. So the definition for the inverse was then that was the definition. So here that's because if you this is the definition for inverse, and if you write then the inverse and the transform should be the same. But these are for orthogonal matrices. And other restriction, not semi-orthogonal, because inverse has only the square matrices. Okay. Next one. With transformation. Yesterday I made the calculation. The three statements are equivalent. The matrix is orthogonal. You take any vector, multiply the vector with the orthogonal matrix, and then the absolute value of it will be the absolute value of the original vector. Here I have this and I have a vector. So what I will get? So the rank of this vector they are the same. I also could do this operation, but I won't. This is interesting. This is going to be very interesting from right now. If Q is an orthogonal matrix and the elements are real numbers, then its determinant is 1. The absolute value of the determinant is 1. Okay, for this example, 0, then it's -1. But I have another example. I hate touchpad. Okay, I have another example, just a moment. No. Do you know Penrose?
What?
Penrose. He got a Nobel Prize, and doesn't matter. He's a very famous cosmologist. But one of the missed theorem that I don't want to tell you is named by him. So somehow I feel that it's terrible. Okay. Yesterday I did these examples. There it's 7.77, and the task was the not that one actually. It was just one above it, before it. The question is which one are orthogonal and which are semi-orthogonal. The first is semi-orthogonal. Trust me, the second is also semi-orthogonal. So if you do the multiplication, you will get also this A2, so two-dimensional identical matrix. The last one is also an orthogonal matrix, and I need this matrix right now because I need these examples. So this is C 1, 7, and 2, 3, 6, 6, 2, minus 3, 3, 2. And if you do the same, divide this into rows and do the multiplication, there will be 0. It could be for you a homework or something like this. This is this example. But here I need its determination. So I calculate the determination of C right now. Here is this. So whatever I will do at the end, I need to divide 7 over 3. So this is 8. Actually, it's better to. No, it's okay. It's 8. Then minus 27. And then minus. This is. This is it. Then minus 36 minus 36 minus 36. And this means okay,
minus 343.
yes, thank you. Minus 343, thank you. Divided by this, it's exactly 1. Minus 1. So, what the statement says is true. Now, you see this. So this, what just mentioned, means the following: the orthogonal matrices do not change the length of the vector. Great. What does it do? The rotational transformations and the mirror transformation. The projection changed it, and everything else changed it. So the statement, every orthogonal matrix is rotational. This reflection is not good, is a mirroring flow line. Mirror, not reflection, mirror, sorry. This is a wrong word. And for n times 2 matrices, we say this is orthogonal 2. There are O3, O4, and everything. Not here, but you also can. Okay, yes. If you have an inversion, the inverse of an orthogonal matrix is its transpose. So, the orthogonal matrix inversion, no, the orthogonal matrix multiplication gives orthogonal matrix. The inversion of the orthogonal matrix gives also orthogonal matrix. And the multiplication of the orthogonal matrix also gives orthogonal matrix. So this set is closed. We have a set which is closed. It has a unit matrix, something, and we have operations above it. It's called group. It's an algebraic term. It's far beyond your necessary knowledge in BSc level. And this closed rotational groups. And this SO, I learned SO2 and 3 in group theory, is good for particle physicists, theoretical particle physicists. You are not a theoretical physicist, but that's interesting, and that's why I decided to stop, because it's far beyond your scope. You learn chemistry and not theoretical physics and practical physics. This is the same. Do you remember the Gram-Schmidt orthogonalization from last semester? That was the very end, just before the eigenvalue problem. It's a basic transformation. Yeah. And it lasted me 50 minutes to do one. With this Gram-Schmidt orthogonalization, you can do the same like you had done with LU decomposition. You do the steps of the Gram-Schmidt orthogonalization, and you note it and do matrices. And then, in the process, gives you two matrices. One is a real matrix, and the R matrix, you have a matrix with real elements, and you can decompose it for the multiplication of two matrices. The first is a semi-orthogonal matrix with the same size of A. R is an upper triangular matrix. What you have to do is the Gram-Schmidt orthogonalization and note and create matrices what you are doing. This is very long stuff. To practice this, we would need 2-3 weeks. We will not do it. Even if I do not repeat at the beginning, it's not enough. So the guy who taught this class made an overshoot. So it's this lesson, this class is too tough for you, for learning chemistry. The responsive person who is responsive, I'm who giving the course, and there is a person who is responsive for the course officially. And he told me, usually that was a discussion with you students, what do you need? Okay, so there is this QR decomposition exists. You have a matrix, and you can create a product of semi-orthogonal matrix and an upper triangular matrix. And this is very useful to fixing system of linear equations, do inversions, and a lot of things. But you do not need this. Against the LU decomposition, this is unique and always exists. This is a thesis. You can check it in the literature if you want. Okay, now the horror comes. We have 25 minutes, sorry for being late again, and it's a new topic. Space over complex field and finite fields. Do you understand what are complex numbers? Imaginary part, real part, and everything. I always told you that these definitions are restricted. I always say real numbers, real spaces, but the elements of the matrix could be matrices, remember block matrices, and it could be also complex numbers. So, this is it right now. To use complex elements in matrices, you face problems. The scalar multiplication does not work for them, and there are a lot of things. First, argument of a complex matrix. This argument is not that argument, and actually I should tell you conjugate transpose. That's the exact term in English. First, what is conjugate? You have a complex number. You remember. So you have C and C is element of C. You can write C as A plus BI, where A, B, element I. You remember this. The conjugate of C is A minus B. These are the same number, just the sign of the imaginary part changes. This is the conjugate. This is an operation. Actually, I can say, what I can say. So this is the conjugation. This is the conjugation. Okay. We have something. This argument is not a good term. I wrote this, but this is not a good term. Hermitian transpose. You have a matrix, conjugate all elements, and then do a transpose. That's the Hermitian transpose. But I have doubt. Perhaps is not Hermitian, it's Hermitian. Do you speak French? No? Do you know that the French cannot pronounce H?
Oh, I didn't know about that.
So if you, for example, the Hungarian's name is Hongrois, and in many language, it's not Hungary, but it's Hungary, and Ungar, so there is no H. In some nation they don't write, some nation they don't just write but don't pronounce. This is one example, funny example. I lived in France, and I looked for a rent, and there was a negotiation with the owner. Oh, and you have to pay for the eating system. The eating system. Do you provide me breakfast? No, the eating system. Eating system. What is eating system? That one. That's the heating system. Yes, the eating system. So perhaps this Hermitian transpose is not Hermitian but Hermitian. So it's funny. But I come to here. And here. So here you have a matrix no, it's okay. Just gone. So if you want to do the transpose, first you do the conjugation everywhere. And then you can do the transpose. Yes. So that in the first row does it in one step, but me, I need two steps. Here you have this, okay, this is funny. You have this matrix If you want to get that one, you first do the conjugation, and then you can do the transpose. So it's too small, I think, but you can see what I mean. You do the conjugate. Do you remember for this conjugate stuff with complex numbers?
Oh,
No, but you then I don't know where you can meet with this conjugate.
oh well, I learned it myself, like there's complex numbers.
Okay. Mother not sets or what?
Not the operation of complex numbers.
Okay. Do you remember the trigonometric form and coordinate form of complex numbers? In physics, you can use complex numbers, you must use complex numbers for the resistance of condensator or what is induction loop. You know the resistance is something I omega L, for example, for a loop, and something. So it's complex. You cannot understand it without without complex numbers. Okay, here. Now you have problem with the scalar numbers because not scalar numbers, scalar product. So you need a new definition. If you multiply two vectors z and w, which elements are complex numbers, then the scalar product is not that we used. You conjugate the first vector and then do the multiplication. And that's not simple. Just a moment, uh-oh, 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 uh-oh. So you have vectors. If you want to do this multiplication, then you have to multiply the conjugate of the first element from the first vector and the second, the first element from the second vector. Then you multiply the conjugate of the second element of the first vector with this with the second element of the second vector. This is what that definition says. Okay, I do it different way. The conjugate of a real number is itself, so that's wait. The conjugate of E is minus E, I. So it means I minus, this is minus 1, so altogether it's 1. So this is exactly which are here. So this is how you are doing the scalar product. Okay, this scalar product has features, properties of the conjugate. If you do this Hermitian transpose twice, you got the same matrix. If you do the Hermitian transpose for a sum of two matrices, then you got the Hermitian transpose of the elements of the sum. Interesting, this multiplying the C, then you got the conjugate of the C multiplied the Hermitian transpose of the matrix. The multiplication of two matrices, the Hermitian transpose of the multiplication of two matrices is the Hermitian transpose of the second and the B. It's like transpose. This is not proved even in the book. The compare scalar product, you have these features. It's okay. Just a moment. For the previous stuff, if I do not consider this C conjugate, this is almost a linear transformation, because you can see the addition, and also the homogeneity is almost you have, but just almost, because it's not C, it's C conjugate. Here, this is the additivity. Here, if this would be C, then it would be a homogeneity, but it isn't. Now, a real mathematician start to think what it does mean and prove some stuff and creates a new branch of the mathematics. But I'm physicist and you are you are studying chemistry, so we don't do it. Scalar product, properties of complex scalar product. It is almost commutative. So the order of the scalar product is almost not important, but we have this conjugate. Is this conjugate stuff makes things more difficult. There is associativity, you can do this, and the associativity for the matrix production I have to check this. Yes, it's okay. I am right. So if you take a complex number and you do this scalar product, then in this case, this is your result. But in this case, here is the conjugate of this C. So it's not so simple. Which is important if you do this complex scalar product and multiply a vector itself, then it's not zero if the vector is not zero. So this is good for calculate the distances and the magnitude of the complex number. That's my remark. The complex matrices has a special subspaces, very nice. There are self-adjuncate matrices if the Hermitian transpose is the same like the original matrix. A self-adjuncate matrix mean diagonal contains some real numbers because the real numbers are equal to their own conjugate. Yes, and all symmetric matrices have an adjugate. Great. Yes, this is what I told you. The complex scalar product allows a definition of distance. You take the u and v vector here. These are in the complex vector space, and the definition is this one. And how you calculate in this proper way, you multiply the u minus v itself and calculate the square root. It's the same like real numbers, just the scalar product is more difficult and the complex numbers are more difficult. And this is also a sign of stop. Cauchy-Bunyakovsky-Schwarz inequality, actually this is inequalation or something like this, the real term. What does it mean? Wait, I think there is a mistake here. No, it's not. Don't mistake. If you take two complex vectors and then their multiplication, I mean complex scalar multiplication, has less or equal length or magnitude, like the length of the u and v vector. Why I say to stop here? Because I learned analysis, mathematical analysis. My professor called it element of mathematical analysis, and I learned it 4 plus 5 hours per week for five semesters, and this inequality appeared in the 4th semester. So this is too much for you in this moment. I have only one slide. The unitary matrix is the complex analog of orthogonal matrices, the real orthogonal matrices. If you have a matrix and its Hermitian transpose multiplied, the original matrix gives identity matrix, then it's unitary matrix. That's the definition. There are some cases. This is the same like in the real orthogonal matrices. This statement was for orthogonal matrices. This is one statement and other statement that we have proved. We have proved this one and proved this one. This unitary matrix is the analog of the orthogonal matrix. Okay, sorry, it's plus 2 minutes. And this is the last slide. This is not material. Perhaps next time I will explain what is it. You go through the complex numbers, and there is, for the left, there is a very simple transformation. Take the number first. Then you calculate the second stuff. You have a C number. Then you do the following transformation. You do this for all points of the complex plane. You do this, and what is the result? This Zn could be divergent. It reaches infinity. But if it's 0, then it's 0. When it's 1, it remains 1. When it's I, it's then I minus 2, minus I. So there is, and those numbers which don't go to the infinity, which are not divergent, are displayed here. That's the model set, and the scale says when these numbers reaches a certain threshold, for example 2, anything could be. So this is the speed of the divergence, and these colors are very nice. And which is important, this is so-called fractal. Its dimension is not 1, not 2, it's something fixed. If you zoom here, for example, you find a very similar set, but it is not the same. And you zoom, and with this color it's beautiful. So why I show this? To balance the mental terror of this stuff that I told you. This is beautiful. Complex numbers are beautiful. The Euler set is a little bit different, the iteration is a little bit different, and depending where you, usually you use a fixed C for the Euler set, and these form, how it looks like, is depend where you take the C number from the complex stuff. So thank you very much. Thank you for coming. It's a very, very familiar and very, very personal practice right now. And the lecture was also one. Okay, thank you very much.